Welcome to class. In this video, we're going to learn how to solve homogeneous systems of linear first-order equations. If you haven't watched the video on systems of equations or on the eigenvalues and eigenvectors, I'd recommend you start there before trying out this one. I think the best way to tackle this one is to learn by doing. So let's start with an example. Here I've got a system of two first-order, linear, homogeneous differential equations. It is linear because on all of my independent variables below, once I've isolated my first-order derivatives, they're already done here, I don't have any independent variables showing up in the coefficients. I know it's homogeneous because I don't have a function of my independent variable left over. In other words, if I were to write this in matrix form, maybe I would say U is the vector xy, and A is the matrix of the coefficients. So here, first equation, first variable, that's x, its coefficient is 1. First equation, second variable, its coefficient is 3. Second equation, first variable is 5. Second equation, second variable is 3. And I'm emphasizing those positions because they tell you where in the matrix the coefficients go. Across the columns are your equation, or excuse me, across the rows are equations, and across the columns are variables. So I've got an x column and a y column, equation 1 row, equation 2 row. Now I'm going to compact all of this into the matrix form of the equation, which is that u prime equals au. And I'm going to move everything to one side here. I'm going to write au minus u prime is equal to vector 0. Remember, this is a vector equation. And the process is the same, actually, of now I've got this first-order linear homogeneous equation. I'm going to convert it to the characteristic equation by replacing nth-order derivatives with nth powers of a dummy variable, say lambda. So here I've got the 0 derivative of u, that's lambda to the 0, times a, minus I've got u prime, or the first derivative of u, which is lambda to the first power, times, well, it looks like nothing, but nothing in matrix land is the identity, right? The identity matrix doesn't do anything when you multiply by it. So I get a minus lambda I equals vector 0. This should be looking familiar here, or awfully suspicious. And it turns out that this is uniquely solved when the determinant of a minus lambda I is 0. So we're trying to solve this matrix equation. And what we saw is that the characteristic equation now boils down to finding eigenvalues. Okay, so the roots, or roots of the characteristic equation, lambda 1 and 2, are the eigenvalues of my matrix A. Those eigenvalues, by the way, happen to be -2 and +6. Now, I would expect x of t, then the scalar function, to have its output be c1 e to the -2t plus d1 e to the 6t, and I'd expect the same format for y. That's why I didn't use c1 and c2 there. I'll have c2 e to the -2t plus d2 e to the 6t. So you'll notice here that if I combine this back into my vector equation, it tells me that u of t should have the form a constant, maybe there's a constant out there, times some vector, call it v1, e to the -2t, plus a constant times some other vector, I'll call it v2, e to the, e to the 6t. all there's left to do is to figure out what the heck are those vectors. But let's take a look at just one portion of this general solution, one fundamental solution, if you will, right? And I'll call this guy vector u1. And that's equal to v1 e to the negative 2t, for example. Let's see what happens when I throw that into my differential equation. Well, I get u1 prime on the left-hand side, and that's going to be negative 2 e to the negative 2t v1 equals, and on the right-hand side, I have a times u, which is e to the negative 2t. Now, the e to the negative 2t's cancel on both sides, and what I get is that my matrix times v1 is negative 2 v1, but wait a minute, negative 2 was an eigenvalue. Oh, so that means v1 must be the eigenvector that goes with negative 2. And in this form, we've actually figured out kind of a general process to tackle this problem. Let me clean up the board and I'll write it down. To wrap up that idea real quick, it all boiled down to the eigenvalues and eigenvectors of A. We know the fundamental solutions have the form e to the lambda 1t v1, so on and so forth, where where the lambda is the eigenvalue and v is the corresponding eigenvector for A. So in our problem, when we were trying to solve this system, we know eigenvalues are negative 2 and 6. The eigenvectors corresponding to those eigenvalues are 1, negative 1, and 3, 5. So the general solution is u of t equals c1 e to the negative 2t times v1 plus c2 e to the 6t times v2. And to help relate that back to scalar world, looking at each of the individual equations, remember u is x, y, and actually I'm just going to ditch my matrices for now. So I've got x and y. If I add up everything across the top rows, I get 1 c1 e to the negative 2t plus 3 c2 e to the 6t. And for y, I get negative c1 e to the negative 2t plus 5 c2 e to the 6t. And in doing this, and so in this way, I don't actually have 4 unique parameters to this system. I only have 2 unique parameters. And we'd expect this because I have 1 unique parameter for each first order equation.